In lecture 35, we're going to be looking at vectors in space. Now, what do I mean by vectors in space? Well, moving from vectors in the plane, which were two-dimensional vectors, to talking about vectors that have three dimensions, vectors that would be in real space and go in a direction of length, width, and possibly even height. The reason we have to introduce this is because the second type of multiplication of vectors that we will discuss requires that we work in three dimensions to be able to understand both what that multiplication means and what kind of applications we might apply. Plus, you could just think in general, if you're thinking about modeling something in the real world, being able to model something in three dimensions is obviously more powerful and more realistic in this in the reality in which we live, in the world in which we will try to model is a three-dimensional world. So, to do that, we got to introduce some new concepts. For one, finding the distance between 2 points in space instead of on just the plane. Representing vectors as position vectors in space, performing operations such as addition, subtraction, and scalar multiplication, and even the dot product. And then to find the angle between two vectors in space. And then another representation of a vector, not just its coordinates or its position vector, but its direction angles. And that's going to be the last thing that we talk about in this section. So first of all, let's introduce the concept of the rectangular coordinate system in three dimensions. So instead of just having two axes, we're going to have a third, and you're going to have to use your imagination here as I draw these to think of this one as coming out towards us. So this would be like the x coordinate. In fact, this is the way that we label them in a mathematics course. This is the x-axis, this is the y-axis, and this is the z-axis. As you'd expect, you'd call this point here at the center the origin. But if you have a point out in space, the question is, how do we find the coordinates of that point? What do we mean by the coordinates of that point? Well, basically what you're going to be looking at is a rectangular prism here that you get by dropping this line straight down to what I will call down in this region here the xy plane, because it's the axes, it's a plane that contains the x and the y axis. It's this flat surface down here. And so if I drop something straight down, and then if from there go straight across parallel to the y axis until I hit the x axis, okay, right there. And do the same thing, go straight back parallel to the x-axis until I hit the y-axis right here. Now I can also, instead of just dropping the point straight down to the xy plane, I could drop it back here to what I would call the yz plane, because that is the plane that contains the y and the z-axis. Now I'm going to drop it straight back parallel to the x-axis until I hit that plane. And you'll see if I drop straight down, I end up at the same place as if I'd gone straight down and then back to the y-axis. If I go back to the yz plane and straight down to the y-axis, I end up in the same place. If I go straight across to the, what we'd call the xz plane, and then drop straight down, I end up in the same direction, same place here. And for both of the x and the y, the xz and the yz planes, if I go parallel to the x-axis back to the z, or parallel to the y-axis back to the z, I end up in the same spot. So you can see where this point is now in space, and what we're going to do is wherever this is, if I call that, say, x1, call this y1, and this value up here z1, wherever they hit those three axes will be the coordinates of that point. All right, so we are able to find the coordinates of a point in space by looking how it projects down onto the xy plane, yz plane, and then xz plane, and then how those then project onto each of the axes, the x-axis, the y-axis, and the z-axis. Now keep in mind, the x-axis is the one that's coming out towards you when we draw this in three dimensions. The y-axis is horizontal, going straight across, and the z-axis is a vertical axis. Okay? And as you learn more about, if you were to go into future classes where you study functions in 3 space, you'll learn that there's a pretty sound mathematical reason why we like the z to be the vertical axis and the x and y to be flat on the plane. It has to do with graphing functions of 2 variables. But For the purposes of this class, we're just going to assume, we're going to take for granted that this is the x-axis coming out towards us, the y-axis going across, and the z-axis going up, and that's how we're going to denote the three coordinates in the 3 space, or in the rectangular coordinate system in space. The next question is, how do I find the distance between 2 points in space? And it doesn't take long to see, and in fact, I'm just going to refer you to the textbook that goes along with this course. There is a description in there about how this formula is derived, but you can see how it's very similar to the distance formula in 2 dimensions. You take the difference in the x's and you square it, plus the distance in the y direction, or the difference in the y's, plus now you just had a third term under the radical, the difference in the z's. So if I were to have left off the z part of this, it would look exactly like the distance formula in 2 space, or in 2 dimensions. Adding the z's is how you find the distance between those 2 points in 3 space. So the distance between 2 points, when they're given in rectangular coordinates, we can then apply that formula directly with this example. You take 4 minus a minus 2 and square it, plus 0 minus 2, square it, plus a negative 3 minus 3 and square it, which would be the square root of, that's 6 squared, plus a negative 2 squared, plus a negative 6 squared, which gives me 36 plus 4 plus 36, which is the square root of 72 plus 4, which is 76. And we could simplify that as a radical. That's 4 times 19. So this would be 2 square roots of 19. Now you recall in 2 dimensions, when we had a vector that we placed at the origin and saw that it extended to some point P, which was x, y, we said then we could write that vector v as x times I plus y times j, where I and j were the unit vectors in the x and y direction, and the x comma y were the actual coordinates of that point. Well, if we now have a 3rd dimension to deal with, we're going to introduce a new vector, which we'll call k, is the unit vector in the z direction. So a vector v that starts at the origin and ends at the point ABC can be represented by this position vector right here, AI plus BJ plus CK. So you represent it now with the 3 coordinates. Now, alternatively, we could also write, and I'll come off to the side here and do this, you could also write V using that angle bracket notation that we introduced as A, comma, B, comma, C. That's not a point, that is a vector. Okay, so if you have 2 points, and you're not starting at the origin, and you want to find the position vector so that the vector goes from point P1 to point P2, but this is now somewhere in space, then you would have 3 coordinates, and it's simply x2 minus x1, y2 minus y1, and z2 minus z1. I'll draw a small little picture here to illustrate this point here, but let's say we've got a point P1 over here that's somewhere above there, and let's say P2 is somewhere back over in this direction. And so this point right here is closer than this point here, so we've got a vector that goes back to that point right there. And I'm saying, let's say the coordinates of this point were x1, y1, z1, and this one is x2, y2. And I'm going to go off the screen here, but just bear with me and say that that is x2, y2, z2. But just looking at just, say, the x's, the change in x from this coordinate to this point is going to be your I. And then if you change from the y's, the z's, so forth, you get these different coordinates for your, or components, I should say, for your vector. So if v goes from p1 to p2 in this example, where p1 is the point -2, -3, positive 0, or just 0, and then p2 is -6, 7, 1, then the vector represented in component form looks like the second point, the end point, minus the first point. So that's a -6 minus a -2, 7 minus a -3, and 1 minus 0. So this becomes -6 plus 2, which is a -4i, plus 7 plus 3, which is 10j, and 1k, that's positive. So this vector goes -4 in the x direction, positive 10 in the y direction, and 1 in the z direction. All arithmetic for three-dimensional vectors is exactly as expected. That is, if you had two vectors, let's say v is a1i plus b1j plus c1k, and w is a2, b2, c2. To add them up, you just add their components. So a1 plus a2, b1 plus b2, and c1 plus c2, right? Just adding like terms is basically what you're doing. To do minus, you subtract. a1 minus a2, b1 minus b2, c1 minus c2. If you want to take vector v, just vector v and multiply it by alpha, that is, I took this times alpha, guess what happens? You just distribute it. So alpha a1, alpha b1, alpha c1. And then last of all, the length of the vector is almost exactly as the length or magnitude it was in 2 dimensions, a1 squared plus b1 squared, but you've got a third component, which is c1 squared. That's how you find the length of the vector. Now I've written these vectors in component form, or in the angle bracket notation, but everything works exactly the same. If I take 3 times my vector v, 3, a -5, and a 2, minus 2 times -2, 3, -2, I'm just going to distribute my 3 inside, so I have 9, -15, and 6, plus, and I'm going to distribute my -2 to each of these, so -2 times -2 is 4. And the reason I changed that to a minus is I'm actually distributing the negative as well. So this just leaves, I'm adding the result of having moved the 2 to everything. So -2 times -2 is positive 4. -2 times 3 is -6. And -2 times -2 again is positive 4. And now I just add these. 9 plus 4 is 13. -15 minus 6 is -21. And 6 plus 4 is 10. There is your resultant vector of taking 3 v's minus 2 w's. To find the magnitude of v plus w, first we're going to add v plus w and then find the magnitude of that resulting vector. 3, -5, 2, plus -2, 3, -2, which would be the magnitude of the vector. 3 plus a minus 2 is a 1. -5 plus 3 is -2. And then 2 plus a -2 is 0. And the magnitude of that would be the square root of the components squared and added together. So 1 squared plus a -2 squared plus 0 squared, which is the square root of 1 plus 4, or the square root of 5. Number, letter C, take the magnitude of v. Magnitude of v would be the square root of 3 squared plus a -5 squared plus 2 squared. And the magnitude of w would be -2 squared plus 3 squared plus a -2 squared. That's square root of 9 plus 25 plus 4 plus the square root of 4 plus 9 plus 4. Now 9 plus 25 is 34. 34 plus 4 is 38. And 4 plus 9 plus 4. 4 plus 9 is 13. 13 plus 4 is 17. Square root is 17. And those do not simplify, so you can't combine any like terms. That's the sum of those two magnitudes. Following the same reasoning that we did back in vectors when we first introduced them in 2-space, we can find a vector that goes in the same direction as a given vector but has only length 1. That's called the unit vector in the direction of v. For any non-zero vector v, to do that, all you got to do is take v and divide it by its magnitude. Or alternatively, think of it as multiplying by 1 over its magnitude times that vector. Same idea. You're just dividing every component of vector v by the magnitude of the whole vector. And what you end up with is you scaled then that vector down to a unit length, but it still goes in the same direction as v. So for example, this one right here, if I want to find a vector that goes in the direction of I plus j plus k, remember this is like 1, 1, 1, you can find the magnitude first of the vector, which would be the square root of 1 squared plus 1 squared plus 1 squared, which is the square root of 3. And now you take 1 over the magnitude times that vector. So you're going to take square root of 3 times I, sorry, not square root of 3, 1 over the square root of 3, I plus j plus k, which, by the way, in better mathematical notation, we'd say this is one over the square root of 3 is square root of 3 over 3, having rationalized the denominator. So this becomes square root of 3 over 3i plus square root of 3 over 3j plus square root of 3 over 3k. Now it looks like a messier vector, but in one sense it's a better vector because it is a unit length. They're better meaning easier to work with and has more applications later on in some applied mathematical courses. So that's the unit vector in the same direction as the v. So really what we're doing is we're extending all the concepts that we learned about vectors to now vectors in space, vectors with 3 dimensions instead of just 2. So dot products of vectors in space would be very similar to what we did with dot products with vectors in 2 dimensions. Namely, we would multiply the x components together, get a1 times a2, plus, and then multiply the b, or the x, sorry, the y vectors together, b1 times b2, and add now these z components, which is c1, c2. The result is still a scalar, and the change from 2 dimensions to 3 dimensions is just an additional term. So the dot product, for example, here is 3 times negative 2 plus a negative 5 times 3 plus a 2 times a negative 2, which is negative 6 minus 15 minus 4, which is a negative 21 minus 4, or negative 25. If you take the dot product of a vector with itself, remember you'll still get the same thing as the magnitude of that vector squared, just like we did in 2-dimensional vectors. That would be negative 2 times negative 2 plus 3 times 3 plus negative 2 times negative 2, which is 4 plus 9 plus 4. 4 plus 9 is 13, plus 4 is 17. All the same properties for dot products hold as in the 2-dimensional case. It's commutative. It distributes. The dot product of a vector with itself is the square of its length, and 0 dotted with any vector. And you can have a 0 vector in 3 space as well. It'd just be 0, 0, 0, or 0i plus 0j plus 0k. And here's more good news. The proof for the angle formula between two vectors holds whether you're in 2 dimensions or 3 dimensions. So the formula is identical. You just have to remember now that in finding the dot product in the numerator, you'll have to do the dot product of 3 dimensions or 3-dimensional vectors, and on bottom you'll have to find the length of 3-dimensional vectors. But ultimately it's exactly the same formula, so you can work these problems the same way. You start by finding v dot w, or for us that's 3 times a negative 2 plus a negative 5 times 3 plus a 2 times a negative 2, which gives me negative 6 minus 15 minus 4, as we've seen before, which happens to be negative 25. Did I have the negative above? Yes, I did. And the magnitude of v is the square root of 3 squared plus a negative 5 squared plus 2 squared, which is the square root of 9 plus 25 plus 4. 9 plus 25 is 34, so the square root of 38. And the magnitude of w is the square root of negative 2 squared plus 3 squared plus negative 2 squared, or the square root of 4 plus 9 plus 4, which is the square root of 17. So cosine of the angle between v and w is v dot w here, right? I'm using this formula up here. V dot w is negative 25 over square root of 38 times square root of 17. So I plug that into my calculator. That's a negative 0.98361. So theta would be the cosine inverse of negative 0.98361. And with my calculator in degree mode, I get 169.6 degrees is the angle between those two vectors. Lastly, we want to describe the direction of a vector in 3 space. Instead of just describing its components, we want to be able to describe what direction it goes in. When you're in 2 dimensions, that's actually pretty simple. You just put it into position form and you say what angle does it make with the positive x-axis. When you have something in 3 space, like you see down here in this picture, what you see is if a vector is coming out in space, you don't uniquely describe a vector by where it or what its angle is relative to just the positive x-axis. What you need is to describe it in terms, or one way to do it is to describe it in terms of its angle that it makes with every axis. So we're going to call these angles direction angles. We'll call alpha the angle between any vector v and I, which is really the vector in the direction of the positive x-axis. Alpha is always going to be between 0 and pi then. Beta is going to be the angle between vector v and j, right? Because that we want to find the vector angle, or direction angle, between the vector and the y-axis. And then gamma, and in case we haven't named these for you before, we'll call that alpha. That's the Greek letter beta, and this is the Greek letter gamma, is the angle between v and k, or the positive z-axis. Now, fortunately, that's actually not very hard to do, since we already know how to find the angle between 2 vectors. Remember that I is just 1, 0, 0. So cosine of alpha would be v dot I over the magnitude of v, the magnitude of I. Now, we have some information we already know. First of all, V is ABC, and I is 1, 0, 0. Right? And the magnitude of V we may not know, we can calculate it, but the magnitude of I is simply 1 because it's a unit vector. So what you end up with is cosine of alpha is the value of A over the magnitude of V. And so it's going to also be true for the rest of these. You can do this exactly the same way with beta and gamma. And so what you end up with is, to find these direction angles, you'll use cosine of alpha equals A over the magnitude of V. Cosine of beta is B over the magnitude of V. And cosine of gamma is C over the magnitude of V. And using these formulas, it's actually fairly easy to verify that the following property is true if alpha, beta, and gamma are direction angles. Then cosine squared of alpha plus cosine squared of beta plus cosine squared of gamma will equal, well, here, let's just kind of think through what this would mean. If I squared this guy right here, I'd get a squared over that, what's inside the square root, right? Or a squared over a squared plus b squared plus c squared, right? If I squared it. Same thing happens here. If I square this one, I would get, let's square it, so you get b squared over a squared plus b squared plus c squared. And if I squared this guy, square it, what do I get? C squared over a squared plus b squared plus c squared. If you add all those three up, you get on the numerator a squared plus b squared plus c squared, because you just add the numerators. In the denominator, it stays the same because they're common denominators. You get a squared plus b squared plus c squared. Add all these things up, you get a squared plus b squared plus c squared over a squared plus b squared plus c squared, which means the square of cosine alpha square plus the square of cosine beta plus the square of cosine gamma is 1. Anytime alpha, beta, gamma are direction angles, this formula right here will always hold. And the last point to make is that any vector can be written in terms of its direction angles. That is, a vector always equals its magnitude times cosine alpha I plus cosine beta j plus cosine gamma k. And the reason I point that out, and again, it's not hard to show from the formulas for the direction angles, the reason I point this out is to say, if you know its magnitude and direction, you can find its component form. If you know its component form, you can find its magnitude and direction. So both pieces of information tell you everything you need to know about a vector. In some applications, one's better than the other. So let's go that one direction where I give you the vector and you find, or the component form, you find its direction angles. All right, so cosine of alpha is going to be a over the magnitude of v. So let's come off to the side here and find the magnitude of v first, since we'll use it all the way through. That's going to be the square root of negative 6 squared plus 12 squared plus 4 squared, which is the square root of 36 plus 144 plus 16. 36 plus 144 is 180. So it's the square root of 196, which is 14. So cosine of alpha would be equal to negative 6 over 14. So alpha is cosine inverse of negative 6/14, or negative, actually 3/7. Which in my calculator gives me 115.4 degrees. Cosine of beta would be b, or 12, over the magnitude of v, which is 14. So beta is the cosine inverse of 6/7, or approximately, using my calculator, 31.0 degrees. And cosine of gamma would be c, or 4 over 14, which means gamma is the cosine inverse of 2/7, or approximately 73.4. Oh, hang on, go back down. We'll just put a box around you. So that's a 73.4, that's a 31.0, and 115.4 degrees. Those are my direction angles. All right, and so that's how we do vectors in space. The last thing we're going to look at in the next lecture is how do we then multiply these vectors in a new way, something called the cross product.